Today, we're diving into what would actually happen if a bomb exploded inside a military or nuclear submarine sitting on the ocean floor, and why this terrifying scenario might be more real, more recent, and more covered up than you think. Okay, so picture this. You're 900 meters below sea level. It's pitch black. You're sitting inside a tube of steel surrounded by silence and pressure. And then, boom, not from outside, from within. Let's break down what that actually means. The ocean keeps secrets better than any vault on Earth. In 2023, unexplained acoustic anomalies were detected in the North Pacific by hydroacoustic monitoring stations. Sounds that matched no known underwater geological event or marine activity. What makes these signals particularly disturbing? They bore striking similarities to submarine implosion signatures, but no nation reported losing a submarine. These underwater acoustic events have specific patterns, explains Dr. Nathan Havers from the Comprehensive Nuclear Test Ban Treaty Organization. We can distinguish between natural events and man-made explosions with remarkable precision. The technology tracking these sounds has evolved dramatically. Advanced AI algorithms now sift through decades of underwater recordings, finding patterns humans missed. These machine learning models are re-examining Cold War submarine disasters, revealing shocking new details about what really happened. Take the USS Scorpion, lost in 1968 with 99 sailors aboard. For decades, the Navy maintained it was likely a mechanical failure. But when AI analyzed the original acoustic data, it identified two distinct explosion patterns, potentially indicating an internal detonation before the catastrophic hull collapse. The first sound signature shows characteristics consistent with a smaller internal explosion, notes former Naval Intelligence Officer, Commander James Whitman. Only after that do we see the catastrophic implosion as the sub sank past crushed depth. Similar forensic audio analysis of Argentina's Aara San Juan, lost in 2017, revealed an acoustic anomaly hours before the final implosion, possibly indicating an onboard fire or explosion that the crew initially survived. But the most chilling question emerging from this new analysis: could some of these accidents have been deliberate? Internal sabotage has always been a nightmare scenario for submarine commanders. During the Cold War, both American and Soviet submarines carried self-destruct charges, not just to scuttle a vessel about to be captured, but potentially to eliminate evidence of covert operations gone wrong. The Russian Kursk disaster in 2000 was officially blamed on a torpedo propellant leak, but some former naval officers question whether the initial explosion might have been triggered intentionally, perhaps to destroy experimental weapons before they could be examined. When a submarine disappears, nations rarely tell the whole story, explains former submarine officer Michael Hansen. The ocean floor is the perfect place to hide evidence, a 2-mile-deep grave that few can access. Could AI soon reveal that what we thought were accidents were actually part of a quiet underwater war? As machine learning gets better at detecting acoustic signatures, decades-old mysteries might finally surface. What's truly disturbing is that we may never know how many submarines are quietly sitting on the ocean floor, destroyed from within, their stories untold. If you're into dark military secrets and deep-sea mysteries, hit that subscribe button. There's more coming that you won't want to miss. A sabotaged sub. The possibility of deliberate submarine destruction isn't just speculation, it's documented military protocol. Declassified Cold War files reveal both superpowers maintained extensive self-destruct systems aboard vessels carrying nuclear weapons or cryptographic intelligence. Operation Chrome Dome included contingencies for nuclear submarines, explains naval historian Dr. Robert Ballard. If capture seemed imminent, preventing technology from falling into enemy hands became the priority, even at the cost of the vessel and crew. These protocols weren't just on paper. Physical mechanisms were installed. The Soviet Union equipped many of their submarines with internal demolition charges specifically designed to destroy sensitive compartments. American submarines carried similar systems, particularly in code rooms and missile bays. The US and USSR both had protocols to scuttle their own nuclear subs in the event of capture. So the idea of an intentional internal blast? It's chilling, but very real. But what if these systems were activated not by command, but by a single crew member? Consider this scenario. A damaged submarine, unable to surface, is being tracked by enemy forces. Capture seems inevitable. One officer, knowing what's at stake, makes the ultimate decision, triggering an internal explosion to ensure state secrets remain secret. This isn't pure fiction. During the Pearl Harbor attack in 1941, the crew of a Japanese midget submarine set off their demolition charges rather than be captured. The partially destroyed hull was later raised by the US Navy, who then secretly dumped it in deeper water to prevent intelligence leaks. More recently, the mysterious fate of the Soviet K-129 in 1968 has fueled theories about internal sabotage. When the CIA secretly retrieved parts of the sub years later in Project Azorian, they reportedly found evidence consistent with an internal explosion, not the mechanical failure officially claimed. What makes these scenarios particularly disturbing is that they challenge our understanding of how submarines are lost. How many other vessels might have met similar fates, their true stories hidden beneath miles of silent water. Minute-by-minute breakdown of the explosion. What exactly happens when a bomb detonates inside a submarine? The sequence is both rapid and devastating. 0, 0, 0, 0. Initial detonation. The bomb explodes, likely in a weapons storage area, like the torpedo bay. In the Kursk disaster, this is precisely what happened. A torpedo's hydrogen peroxide fuel leaked and ignited. The pressure wave moves at supersonic speed through the confined metal tube. 003. Overpressure wave. Within 3 seconds, the shock wave reaches every compartment. Steel bulkheads buckle. The overpressure ruptures lungs and eardrums instantly. Any crew in the forward compartments would have no time to react. The pressure wave in a confined space like a submarine would be amplified by the rigid hull, explains explosives engineer Dr. Sandra Reyes. What might be survivable in open air becomes instantly lethal underwater. 0010. Fireball and oxygen depletion. The explosion creates an intense fireball that rapidly consumes available oxygen. Temperatures reach over 3,000 degrees Celsius, melting equipment and igniting secondary fires. Electrical systems fail as cables melt and short-circuit. 0030. Hull breach and flooding, the pressure hull, designed to withstand external pressure, not internal explosions. Ruptures. In the Kursk case, the second explosion tore a hole the size of a house in the forward hull. Ice-cold seawater rushes in at terrifying pressure. At 900 meters depth, water enters at roughly 90 atmospheres, equivalent to being hit by a high-speed train. 1 a.m. Progressive flooding and potential survivors. If any watertight compartments remain intact, crew members there face a grim situation. In the Kursk disaster, 23 sailors initially survived in the aft section. They had no power, rapidly dropping temperatures and limited oxygen. The flooding advances compartment by compartment as weakened bulkheads fail under water pressure. You have maybe 60 seconds between a bomb going off and your sub becoming an underwater tomb. This isn't Hollywood. These are real protocols, real physics, and real lives. For nuclear submarines, the nightmare continues long after the human tragedy. When nuclear material is involved, either from weapons or the reactor, the explosion creates what scientists call a plutonium puddle. As the metals cool in the frigid deep water, they form a radioactive hotspot on the ocean floor. Plutonium has a half-life of 24,000 years, warns marine radiologist Dr. Elena Korsakov. These sunken submarines create toxic reservoirs that will outlast our civilization. The Komsomolets submarine, which sank in 1989 following an internal explosion, has been leaking radiation for decades. Measurements near its damaged hull show radiation levels nearly 800,000 times higher than normal seawater. While the vast ocean dilutes this contamination quickly, the wreck site itself remains a concentrated danger zone. And if that sounds bad, wait until you hear what might be leaking out of these wrecks decades later. Ghosts on the seabed, long-term environmental fallout. These submarine disasters don't end when the last air bubble escapes the hull. They transform into slow-motion environmental catastrophes playing out over centuries on the ocean floor. The Soviet nuclear submarine Komsomolets sank in 1989 after an internal fire and explosion. Today, over 3 decades later, it sits 1,680 meters deep in the Norwegian Sea, silently leaking its poison. Scientific expeditions have measured cesium-137 levels near the submarine's damaged ventilation pipe at 800,000 times higher than normal seawater. What we're seeing with these nuclear submarine wrecks is unprecedented in human history, explains marine ecologist Dr. Mikhail Zhukov. We've created radioactive islands in some of the most remote environments on Earth. Each nuclear submarine wreck becomes what scientists now call a silent reef of plutonium, a toxic structure where the nuclear materials slowly corrode and integrate with the surrounding ecosystem. Fish and deep-sea organisms absorb these radionuclides, potentially carrying them into the food chain. When the Norwegian research vessel Aegir surveyed the Komsomolets wreck in 2019, they discovered something alarming. Radiation wasn't leaking steadily, but in unpredictable pulses. This suggests that as the hull continues to deteriorate, sudden releases of trapped radioactive material could occur. These submarines weren't designed to be underwater tombs for nuclear material, warns nuclear safety expert Dr. Jana Viktorsson. Their containment systems were meant to last decades, not centuries. Across the world's oceans, there are at least 8 confirmed nuclear submarines lying on the seabed, what researchers now grimly call cold graveyards. Most remain unmarked and unmonitored, their exact locations sometimes known only to a handful of military officials. The USS Thresher and Scorpion, the Soviet K-8, K-219, and Komsomolets, the Russian Kursk, each contains nuclear material that will remain dangerous for thousands of years. And these are just the ones we know about. We always think fallout means clouds, sirens, Geiger counters. But at the bottom of the ocean, fallout looks more like rusted metal and a silence that will outlive us all. Plutonium-239, found in nuclear warheads, has a half-life of 24,100 years. The reactor cores contain uranium-235 with a half-life of 703 million years. This means these underwater radiation zones will exist long after our civilization is gone. While the vast ocean dilutes this contamination, scientists worry about what happens as these hulls eventually disintegrate completely. Will we see concentrated plutonium puddles form in the sediment? Could underwater currents eventually disperse these materials more widely? Russian attempts to seal the Komsomolets reactor with special polymers in the 1990s have already failed. The Bellona Foundation, which monitors nuclear contamination, has documented increasing radiation levels around the wreck, suggesting our current containment strategies are inadequate for the timescales involved. But here's the question: has this already happened? The real incidents: Kursk, Scorpion, Komsomolets. The nightmare scenario of an internal explosion destroying a submarine isn't theoretical, it's historical fact. multiple nuclear submarines have been lost precisely this way, their stories revealing just how devastating such events can be. The Russian K-141 Kursk disaster in August 2000 represents perhaps the most thoroughly documented case. During naval exercises in the Barents Sea, a faulty torpedo leaked highly volatile hydrogen peroxide fuel in the forward compartment. The resulting explosion blew open the torpedo tube and ripped through the first compartments. Just 135 seconds later, the fires detonated additional torpedo warheads, causing a secondary explosion measuring 4.2 on the Richter scale, equivalent to about 3 to 7 tons of TNT. The massive blast tore a house-sized hole in the submarine's bow, sending the 154-meter vessel and its 118 sailors plummeting to the seafloor 108 meters below. Acoustic data captured by Norwegian seismic stations recorded both explosions in chilling detail, first a smaller blast, then the catastrophic detonation that doomed the submarine. The acoustic signature of the Kursk disaster is now the reference point for identifying submarine explosion events, explains underwater acoustics specialist Dr. Henrik Larsson. It has a very specific pattern that differs from natural phenomena. Even more mysterious is the case of USS Scorpion, lost in 1968 with 99 sailors aboard. The American nuclear submarine disappeared in the Atlantic under still disputed circumstances. Declassified Navy documents reveal that acoustic sensors detected 2 separate explosive events, consistent with an internal detonation followed by hull collapse. Former Navy Admiral John Poindexter later revealed the most likely explanation was that a torpedo accidentally activated inside the submarine. Whether through battery failure or propellant ignition, the weapon that was meant to protect the submarine instead destroyed it from within. Perhaps most troubling is the Soviet K-278 Komsomolets, which sank in 1989 after a fire broke out in the aft compartments. As the submarine descended uncontrollably, something exploded inside, punching a massive 20-square-meter hole through the forward pressure hull. Experts believe this was likely hydrogen gas from seawater reacting with the sub's batteries, or potentially a torpedo warhead detonating as water pressure crushed the hull. The extraordinary lengths nations go to recover these destroyed submarines speaks to their strategic importance. The CIA's Project Azorian in 1974 remains one of the most expensive and ambitious covert operations in history, spending over $800 million, equivalent to billions today, to secretly raise parts of the Soviet K-129 submarine from 5 kilometers deep in the Pacific. Using the purpose-built Hughes Glomar Explorer ship, disguised as a deep-sea mining vessel, they managed to recover part of the submarine, including 2 nuclear-tipped torpedoes and the remains of Soviet sailors, all while maintaining a cover story about manganese nodule mining. When a nation spends that kind of money and risk to recover a submarine wreck, notes former intelligence analyst Richard Thompson, you have to ask what they're trying to find or what they're trying to hide. Surveillance. Could we detect the next one? In the depths of the ocean, a complex web of underwater microphones listens constantly. These hydrophone arrays, established during the Cold War and expanded since, form what might be the planet's most sophisticated surveillance system. The U.S. Navy's Sound Surveillance System. SOSUS consists of strings of highly sensitive underwater microphones strategically placed across ocean basins. Originally designed to track Soviet submarines, this network can detect acoustic events thousands of kilometers away. These systems are incredibly sensitive, explains former Navy acoustic analyst Dr. Catherine Williams. They can distinguish between different submarine propeller designs, identify whale species by their calls, and pinpoint underwater explosions with remarkable precision. Complementing SOSUS is the International Monitoring System operated by the Comprehensive Nuclear Test Ban Treaty Organization, CTBTO. This civilian network includes 11 hydroacoustic stations specifically designed to detect underwater nuclear tests, but they pick up much more. The CTBTO stations detected the implosion of the Argentine submarine A San Juan in 2017 from over 6,000 kilometers away, notes underwater acoustics expert Dr. Mario Zampoli. The system registered the sound of the submarine's pressure hull collapsing under 3,000 tons of water pressure. What's disturbing is that these systems regularly detect unexplained underwater acoustic events, classified as non-seismic events, that don't match known patterns. According to leaked reports from maritime intelligence agencies, these anomalous sounds are logged monthly. Some are eventually identified as underwater landslides or volcanic activity. Others remain mysterious. Could some be submarines meeting violent ends, far from prying eyes? Think about it. We track whales across oceans. We hear underwater landslides. But can we hear the exact moment a steel coffin explodes? Maybe. The scarier thought, maybe not. Despite this technology, there remain vast gaps in coverage, particularly in the southern oceans and parts of the Pacific. A submarine could potentially vanish in these acoustic blind spots without triggering global detection systems. More troubling is the possibility that some nations might recognize these acoustic signatures but choose to keep them classified, either to protect intelligence sources or to avoid diplomatic incidents. In 2023, a Russian Akula-class submarine reportedly went missing during exercises in the Barents Sea. After 3 days of silence, it reappeared, with Russian officials claiming communications equipment failure. But analysts noted unusual acoustic signals during this period, potentially indicating an onboard emergency that was successfully contained but never acknowledged. The slow burn theory emerging from acoustic experts is chilling. There may already have been submarine disasters we simply don't know about. Steel coffins resting silently on the seafloor, their destruction masked by ocean depths and government secrecy. What happens after the blast? After a submarine is destroyed by an internal explosion, the aftermath unfolds in stages, from immediate military response to decades-long environmental monitoring. First comes the search. When the Kursk sank in 2000, Russia initially refused international assistance, losing precious days when survivors might still have been rescued. By the time Norwegian divers reached the wreck, all 118 crew members had perished, including 23 men who survived the initial explosions but died waiting for rescue. The window for submarine rescue is brutally short, explains former submarine rescue specialist Commander James Oberg. Within hours, oxygen depletes, temperatures drop, and carbon dioxide levels become lethal. Then comes the agonizing decision: recover the wreck or leave it as a war grave. The Kursk salvage operation in 2001 was unprecedented. A Dutch-led team, Mammoet Smit, amputated the damaged bow section using giant cutting wires, then attached cables through holes cut in the pressure hull to lift the 9,000-ton main hull. The technical challenges were enormous. We were attempting something never done before, recalled salvage master Sergei Balyasnikov, raising a nuclear submarine from the seabed while ensuring its reactor and weapons remained stable. The operation cost over $65 million and required custom-built equipment. When they finally delivered the Kursk to dry dock in October 2001, it became the heaviest object ever lifted from such depth. Not all submarines meet this fate. The CIA's Project Azorian attempted to recover the Soviet K-129 from 16,500 feet deep, over 3 times deeper than any previous salvage. Despite spending the equivalent of billions in today's dollars, they only recovered a portion of the front section before the rest broke off and returned to the depths. For submarines left on the seabed, environmental monitoring becomes a generational responsibility. The Bellona Foundation, an independent environmental organization, has tracked radiation leakage from the Komsomolet's wreck for decades. Their findings are concerning. Radiation levels near the submarine periodically spike as new cracks develop in the corroding hull. These wrecks require constant vigilance, warns nuclear safety inspector Dr. Niels Bohmer. We're talking about monitoring timescales that exceed the lifespan of governments, let alone individual careers. Do military forces secretly monitor these sites? Submarine tracking expert Peter Lobner believes they do. There's evidence that both Russian and American assets periodically visit these wreck sites. They're checking for signs of tampering or salvage attempts by other nations. Beyond the strategic and environmental concerns lies a more human reality. Each sunken submarine is also a war grave. The USS Scorpion, USS Thresher, and numerous Soviet submarines contain the remains of hundreds of sailors who never returned home. When we discuss these wrecks in technical terms, we sometimes forget their tombs, notes naval historian Dr. Richard Compton Hall. The Kursk recovery operation returned the bodies of 115 sailors to their families for proper burial, providing closure after unimaginable tragedy. The science of internal implosion. Now that we've explored the historical cases and aftermath, let's examine the physics that make an internal explosion inside a submarine so catastrophic. Submarines are essentially pressure vessels, designed to withstand enormous external pressure while maintaining normal atmospheric conditions inside. A modern nuclear submarine can dive to around 500 meters, where water pressure exceeds 50 atmospheres or 735 pounds per square inch. Submarine hulls are engineering marvels, explains naval architect Professor Andrew Marshall. They're designed as perfect cylinders because this shape distributes external pressure evenly across the structure. But this design has a critical vulnerability. It's optimized against external compression, not internal explosion. When a bomb detonates inside a submarine, the pressure wave has nowhere to dissipate. It reflects off the rigid hull, amplifying the destructive force. Think of it like this. If you squeeze a balloon from all sides, it compresses evenly until reaching its limit. But put a small explosion inside that balloon, and it ruptures catastrophically because the force pushes outward against a structure designed to resist inward pressure. The confined space creates what we call pressure multiplication, explains explosion dynamics researcher Dr. Elise Chen. The shockwave bounces off interior surfaces, creating complex reflection patterns that can increase peak pressures by 10 to 20 times compared to the same explosion in open air. The Kursk disaster demonstrated this horrifically. The initial torpedo explosion, estimated at only 50 to 100 kilograms of TNT equivalent, was enough to breach the internal bulkhead and trigger a chain reaction that ultimately destroyed the entire forward section of the submarine. Water pressure adds another deadly dimension. Once the hull is breached, the external pressure, potentially hundreds of atmospheres at depth, drives water in at tremendous velocity. This creates a water hammer effect, where the incompressible fluid slams into interior structures with devastating force. The final phase is perhaps the most terrifying, the progressive collapse. As water floods into damaged compartments, the submarine begins to sink deeper. At some point, it will reach its crush depth, where even intact sections can no longer withstand the external pressure. When a submarine exceeds crush depth, the implosion is nearly instantaneous, notes deep-sea physics expert Dr. James Cameron. The hull collapses at nearly the speed of sound underwater, about 1,500 meters per second. Anyone inside would experience death so quickly their brains wouldn't even register the event. This sequence creates a distinctive acoustic signature that underwater monitoring stations can detect. First the explosion, then a series of cracking sounds as bulkheads fail, and finally the thunderous implosion as the hull collapses. The physics of these events explains why internal explosions are so much deadlier than external ones. Submarines are designed to survive underwater explosions at a distance. Their rounded hulls deflect shock waves, but they have almost no defense against explosions from within. While we've covered some major submarine disasters, several other historical cases provide crucial context for understanding internal submarine explosions. The loss of Argentina's ARA San Juan in 2017 remains one of the most recent and thoroughly documented submarine disasters. The diesel-electric submarine disappeared during a routine transit from Ushuaia to Mar del Plata, with 44 crew members aboard. For 2 weeks, an international search operation found no trace of the vessel. The breakthrough came from an unexpected source. The Comprehensive Nuclear Test Ban Treaty Organization's hydroacoustic station, HA-10, near Ascension Island, detected an unusual sound signature on November 15, 2017. What the hydrophones picked up was unmistakable, explains Argentine Navy Captain Gabriel Galeazzi. An impulsive acoustic anomaly consistent with an underwater implosion. When the wreck was finally located a year later at 907 meters depth, the evidence confirmed the worst fears. The submarine's hull had catastrophically collapsed inward. Investigation revealed that seawater had likely entered through the submarine's snorkel and caused a short circuit in the forward battery bank, triggering a fire that led to an internal explosion. This evidence matched precisely what the acoustic sensors had detected. First, a smaller explosion, then the catastrophic implosion as the damaged submarine sank below crushed depth. The use of internal explosives to destroy submarines has historical precedents dating back to World War II. During the Pearl Harbor attack in 1941, Japanese midget submarines carried demolition charges specifically designed for self-destruction if capture seemed imminent. One such mini-sub was discovered by the U.S. Navy in 1960, partially destroyed by its own scuttling charge. The crew had activated the demolition system when their vessel became trapped in shallow water. The Navy quietly raised this wreck and disposed of it in deeper water to prevent technical information from falling into unwanted hands. These scuttling charges were standard equipment, notes naval historian Dr. Timothy Mulligan. They represented the extreme measures navies would take to protect their technology and prevent capture. Perhaps the most important legacy of submarine disasters is the USS Thresher tragedy in 1963. Though not caused by an explosion, this accident, which claimed 129 lives when the nuclear submarine imploded during deep diving tests, revolutionized submarine safety. The Thresher disaster led directly to the SubSafe program, the U.S. Navy's comprehensive submarine safety system that fundamentally changed how vessels are designed, built, and maintained. This program focuses on maintaining hull integrity and ensuring emergency systems can function even during catastrophic failures. SubSafe was born from tragedy, explains former Naval Sea Systems Command Engineer Dr. Richard Walsh. It's arguably the most successful safety program in maritime history. No SubSafe certified submarine has ever been lost. These disasters also spurred development of advanced submarine rescue technologies. Modern deep-sea rescue vehicles can now attach to submarine escape hatches at depths exceeding 600 meters, providing a survival pathway that didn't exist during earlier accidents. The International Submarine Escape and Rescue Liaison Office now coordinates global submarine rescue capabilities, ensuring that no matter which nation loses a submarine, international assistance can rapidly deploy specialized equipment. These improvements represent hard-learned lessons, each advance in submarine safety written in the blood of sailors lost to the depths. Yet, despite these measures, the fundamental vulnerability remains. An internal explosion at depth is among the most difficult scenarios for any crew to survive. We've descended through layers of history, science, and secrecy to answer a chilling question. What happens when a bomb explodes inside a submarine at the bottom of the ocean? The answer is unequivocal. It's nearly always fatal. The combination of confined space, pressure amplification, and the unforgiving ocean environment creates a perfect storm of destructive forces. From the initial blast to the catastrophic implosion, the timeline unfolds in mere minutes, often leaving no survivors. While the sensationalist idea of submarine explosions creating massive tsunamis is largely myth, Operation Wigwam showed even a 30-kiloton nuclear depth charge produced minimal surface disturbance. The true danger is more insidious. What we're left with is an invisible crisis beneath the waves. Scattered radiation hotspots, slowly leaking nuclear materials, and environmental contamination that will persist for millennia. The Komsomolets wreck alone is expected to remain dangerous for the next 20,000 years. Perhaps most disturbing is what we don't know. How many unacknowledged submarine disasters lie hidden in classified files? How many unexplained acoustic anomalies represent vessels lost to internal explosions? The deep ocean keeps its secrets well. The submarines we've discussed, Kursk, Scorpion, Komsomolets, San Juan, represent confirmed cases where evidence eventually surfaced. But for every known disaster, naval experts suspect there are others that remain officially unacknowledged, their wrecks resting silently on distant seabeds. Some wrecks never rust away. Some secrets never surface. And somewhere in the world right now, submarines patrol the depths carrying the same volatile mix of weapons, nuclear materials, and human vulnerability that has led to tragedy before, and almost certainly will again. If you made it this far, you know how deep this rabbit hole goes. Subscribe for more. We're just getting started.